1 second, and thousands of stars are born and die in the universe. 1 second, and Google receives 3 million inquiries. 1 second, and each person generates 1.5 megabytes of data on average. The importance of data, as well as its speed and volume, keeps growing. The Riga TV tower is the tallest TV tower in the European Union. In just 20 years, it has become the most important internet connection hub for Latvia. And not only. As communications operators, authorities, and each and every person increasingly demand more secure data transmission and storage services, the tower now offers the latest Tier 3 data center. It means more floor space, megawatts of power, and petabytes of data, but most importantly, a connection close to all global digital resources for all of our customers. If you are in the tower, you are everywhere. Its power and connection diversity open the doors to the European and global data metropolises. As people need solutions, not just technologies, we offer software for the remote management of networks, operations, and businesses with 24/7 customer assistance. The software visualizes data processing and storage resources, allowing us to offer more standalone virtual servers from the same location, enabling private access and solution flexibility for each and every customer, as well as unprecedented efficiency, including energy efficiency. While your hardware enjoys our climate, you are able to reap the economic benefits of our solution. We invite local authorities and businesses, as well as foreign businesses interested in the quality and security offered by the unique combination of the infrastructure and personal capacity to visit us. We are visionaries of IT solutions that already power huge data transmission capacities in the entire world and are able to connect to any place on the planet. See you in the Riga TV tower, as 1 second will become more and more important.
Thank you. This is where a round of applause goes. Thank you. So before I start to announce people on the stage, let us repeat some very important acronyms. Quantum key distribution, which is QKD, and Post-Quantum Cryptography, which will be also mentioned on stage, PQC. So, please welcome now the moderator of the event to take place. Please, leading QKD engineer of Latvia State Radio and Television Center, Leo Truksans. Leo, welcome to the stage. This is your chair. Then 5G program manager for NATO Cooperative Cyber Defense Center of Excellence, Mattias Männi. Welcome. Future Programs Officer of European Space Agency, Kokkonis. Member of the Board of Latvia State Radio and Television Center, Evijs Taube. Cryptography researcher and scientist at AIT, or Austrian Institute of Technology. Please welcome Christoph Striks. Associate Professor of University of Latvia, Aleksandrs Belovs. That's our panel. You can still use opportunity to ask questions. It's live.5gtechreatory.com where to do it. And now, Leo, welcome.
Thank you. We start this discussion with Evijs Taube. I know that LVRTC company has historically had background in broadcast infrastructure, but in last decades, has been active in providing new services. So what brings LVRTC to quantum technology? Why this is important?
Yeah, thank you, Leo. And first of all, thanks to the audience for the big crowd. We had the last year, 3 times smaller room, and it's nice to see that it's growing. And also I know remotely there are many listeners, so also hello to them. But as a short intro from the company, of course we can have a separate session for that. The heritage is a television radio, as the misleading name states, but there are many others. And one important part is the critical communications. That's basically why we are talking about the quantum cryptography and the quantum altogether. But let me tell you a very short side story. We are having not only the panel, but we had also the full session with 3 hour, I don't know, 10 presentations, was it? In the morning, and it was a full room. And at the end of that session, we have signed a memorandum with 11 organizations of Latvia. And there is, of course, much more than QKD. There are quantum computing, sensors, radars, etc., etc. So it's very wide. But the memorandum, what we have signed, that covers basically many areas. And the fun fact is that there are many Latvian startups. There are academia, scientists, and all of them are working within Europe, many connections and different organizations, different units, EU, NATO, different programs, academia, networks. And it's very nice to meet in a big cities like Brussels or Paris or whatever. But that's, I think, very excellent to meet in Riga. So we are here, and we all know, as Latvians, we know that Latvians are everywhere. There even is a nice book, Latvians Are Everywhere. I'm not promoting, but there are many stories like Forrest Gump stories about Latvians. But anyway, it's very nice to be in Riga. And that's why we are here. I'm proud to present LVRTC as we are hosting this event and bringing people together. We call it critical mass. Thanks.
Okay, thank you. Here in the panel discussion, we mostly have experts in the field of communications and secure communications. But Aleksandrs is an associate professor at the University of Latvia, particularly in field of quantum computer algorithms. So what would you say, where lies the power of quantum computers and how those computers will challenge the cryptography that we know today?
Okay, thank you, Well. So when talking about cryptography, it's important to understand that there are 2 different realms of cryptography that are vastly different. So the one is symmetric cryptography and the second one is asymmetric cryptography, also known as a public key cryptography. So talking about symmetric cryptography, it's a very old concept going back from the ancient times. And so the idea there are 2 persons and they want to communicate securely and they have a common key that is known only to them and that's the same key. Okay, and talking about symmetric cryptography, so like modern things would be like DES or IES and descendants. So that particular realm is somewhat secure from quantum attacks. So you can still use it, so no one knows how to use quantum to break it. But for the asymmetric cryptography, it's a completely different story. So the asymmetric cryptography has 2 keys. So one is private and another one is public. So public is, as you can guess, is known to anyone. And so the idea is that anyone can encrypt and send a message to the recipient, but only the recipient can decrypt because he knows the private key. And so theoretically, it's possible, it's always possible to get the private key, so that's an important thing from the public key, but the trick is that it's computationally inefficient. So for instance, the 2 best known schemes are RSA and elliptic curve cryptography. So they are both based on problems that we think are hard, so no one knows how to solve them efficiently. So that would be factoring integers in the case of RSA and solving discrete logarithm in the case of elliptic curve cryptography. Okay, and the problem with these 2 particular things that both of them, it's quite interesting with that both of them are really not secure against the same quantum algorithm due to Peter Shor, who developed it in the 90s. And so, yeah, so, but on the other thing, that is the best well-tested schemes classically. So people really trust them. And they, especially the elliptic cryptography now, they have very short public keys and very fast realization that is important, especially for embedded devices where the power consumption is a big issue, and so people are hesitant to move away from these schemes. Okay, but whenever anyone has a quantum computer that is sufficiently powerful, they can break any of these schemes, so that's the problem.
Okay, thank you. Christoph, you come from Austrian Institute of Technology, which is well known for being one of the leading centers for QKD and other quantum technologies. Perhaps you could tell us what is QKD and how do we integrate it with classical technologies?
So, yeah, there it is, QKD, and you mean also post-quantum cryptography, right?
Yes.
To integrate. Okay, so the two abbreviations in one question. So first of all, hello to everybody here, and also hello to everybody online. It's a pleasure to be here, coming from Austria, from Vienna. And let me point out what I expect. So first of all, there's currently so much going on in the realm, in quantum in general, but also in the so-called quantum key distribution world or quantum communication in general. So quantum key distribution uses physical effects between two entities to securely exchange a key. So this key can be used between them to later encrypt data and even used for further authentication measures. So as Alex said before, there is another realm, which is called post-quantum cryptography, PQC. They both, I will go into detail in a bit, they can complement each other. But first of all, I have to emphasize the risk of a quantum computer here as well, as a cryptographer. So what it means is, it was perfectly pointed out, there's an algorithm which will break the cryptography used in many of your devices, in many of your communication systems today, ranging from sending messages over Signal or WhatsApp to our financial data. So these algorithms are at risk today because of the algorithm developed by Peter Shor in the 90s. Currently, what we see, there are the two dimensions, the two ways to go, which are called the PQC and the QKD. They are both the abbreviations again. And this is what we will foresee in the future. What I believe is that both PQC and QKD will complement each other, will go not only in their own isolated fields, but they can complement each other. They can work perfectly together. And this concept is called hybridization, between PQC and QKD, essentially using distributing a secure channel between two entities over PQC and the secure channel over QKD. And in the end, at the source and the sender and the receiver at the end, the key is combined again. So if one attacker is on the QKD line, it cannot break the key because it's still protected by PQC. On the other side, if one attacker is on the PQC line and tries to get out, breaks the post-quantum cryptography, we still have the guarantees of the QKD. I cannot emphasize this enough. So that's why I expect in the future that for large-scale quantum-safe networks, and I believe we come to EuroQCI later, which is going to be a quantum communication infrastructure all over Europe, for such networks, a combination of PQC and QKD would be beneficial.
Okay, thank you. Mattias, you are also a researcher in secure communications in certain industries. How would you tell what are the current possibilities of quantum applications in communications? Where are we now? What can we do with that?
Yes, hello. Being a networking guy on the stage here and not a quantum guy really, then and dealing with research on communication technology platforms, I struggled to put these two topics together, and with my engineering head, I was thinking of a parallel that it's like we have a universe, which we know, which is all around us. We've been exploring it for a while, and then suddenly we are talking about some metaverse, which is like another universe inside of the universe in a way. So in a way, we have the same effect here, that we have an established networking base, kind of like a universe, and then we can put the quantum, which is even bigger than the existing scene, on top of here, or we start to embed them in a way. In our research on the primary domain or path, so to say, if I, for instance, should bring a parallel to the relations to 5G research we do, we struggle with challenges like, something is described in 3GPP release 16, great, that's probably to some extent available in practice as well in the nodes we use for research purposes and in commercial domain as well out there. But then there is loads of security-specific features that come in release 17, release 18, release 19, and some of the features we really look forward to in terms of to prove the good security design are even left for the 6G. So thinking on that path and having a practical approach to research, because what we do, we want to take into usage in everyday exercises, we carry all that. We can only do that with the equipment at hand that is really usable and configurable, and thinking how far we are from what we would like to see in terms of having them standardized, and then how big is the gap, what's available today in terms of from vendors, what's implemented in the nodes. And then now thinking, okay, but the quantum domain is also next here, should somehow integrate to that. I think it feels, for an average networking guy, it feels very far away. On the other hand, there is practical usage of that in the fiber connections. I guess the setup is already, to some extent at least, usable for in integration with the DWDM systems. And that's also it can be an underlying level for the 5G environment to be used. So in a way, I was describing that it's very far, and with the other example, it's already here and available. So this is where we are at the moment, in very short.
Okay, thank you. Just a quick remark for the audience. I think Mattias is more than, how did you put it, simple networking guy. So let me continue. Zois, you are with the European Space Agency. How do you see quantum technologies coming to space area?
I think there is a very good overlap of quantum technologies and space in different directions. And first of all, I think we're talking very much, we are looking at quantum computing as a threat. I think we should first see quantum computing as an exciting opportunity, and I believe that Alexander would very much agree with me, because, okay, it's breaking, or it has the potential to break current cryptographic algorithms, yes, but it has also the potential to help us address serious problems. So the first aspect where space has a very large interest for quantum computing is exactly in such problems, in terms of mission planning, in handling data that are coming from space, and so on. On the other side, space can offer an experimentation environment for understanding quantum better than we do now, because there are different conditions, larger distances, different gravitational fields, and so on, which allows us to study quantum better. Now, coming a little bit more into the quantum cryptography and security-related aspects, space can support quantum key distribution, and that is a way, that is something that is maybe a little bit technical. Normally, what is used to exchange quantum keys and exchange quantum information in general is fiber optics, and the attenuation or the loss in fiber optics is higher than the loss in free space. That means that you can achieve much higher distances if you are using satellite communication, which allows to scale in terms of distance, quantum Q distribution to a much larger extent, so that you do not have quantum secure channel between two cities in the same country, but worldwide potentially. So that would be one aspect. On the flip side, it is very important to understand that the space assets and the satellite communications are an integral part of what we are using for our regular communication. That means that we need to ensure that these are also secured against quantum computing capability that would break the current algorithms. This is a couple of subtle aspects on that, because somebody could, of course, argue that quantum computers are not yet there, so why do we care? But there is a commonly mentioned threat about that, which says, capture the data now, store it, and once the quantum computer is there, you can break the cryptography and read it. Now, if we look to the fact that space assets have a relatively long lifetime, so the satellites are standing there for a long time, you need to do a lot of preparation and so on, it is quite likely that you need to start preparing now for the assets that will be there in the future. So that would be in a short wrap-up.
Okay.
Thank you.
Thank you. Christoph, you were also having a talk today during the presentations about the projects that you do in Austria and the QKD authentication problem. Could you describe us more, why is this a problem and how are you tackling it?
Yeah. So when we think usually about QKD, we think of Alice and Bob. Yeah? They're connected via a classical channel and via a quantum channel. And they exchange information and they establish a key only known to both of them. The problem is here, before starting QKD, you have to authenticate each other, which means this. Does Alice know who Bob is? Does Bob know who Alice is? Yeah? If you have only one link, Alice and Bob are directly connected, this is no problem. You can solve this with so-called pre-shared keys. You establish keys beforehand, then you do QKD and so on. So right now, QKD needs authentication in the beginning, and this is done when you have only a few devices, it's no problem. But now the thing comes in when you think of larger networks, like, as I said before, the EuroQCI, which consists of several nodes, and they want to communicate each other. The member states want to communicate each other. Vienna wants to communicate with Riga and so on. And we need trusted node in between because QKD has this range limit. So how is it possible that Vienna can authenticate to Riga and vice versa? And this is essentially the authentication problem in QKD, which is not that easily solvable. It can be solved inefficiently, with also pre-shared keys. Vienna and Riga exchange a key beforehand, only known to both of them, and then they can do a QKD. But now think about several other cities in Europe and so on. Each has to have unique keys with each other. So this is very inefficient. Also, when the network changes, what is happening? Also, when some node gets down, some node gets up again, must be introduced into the network. So this is essentially what we call the QKD authentication problem. And here as well, there's at least one efficient solution to that is also use post-quantum cryptography as a second channel, essentially, as well. It also gives you end-to-end authentication in that sense. And that's also a reason why I believe this is the combination of PQC, because PQC runs on classical networks, right, on classical computers, and QKD on the new quantum devices can benefit from each other. Yes.
Okay, then I will turn back to Alexander's, our algorithm expert. So how could you explain it in simple words, how PQC saves us from quantum threat?
Okay, since PQC, it's post-quantum cryptography. So this means a cryptography that is supposed to be secure when we have a full-scale quantum computers. So as I said when I talked about previously about RSA and elliptic curve cryptography, that they are built upon or rely on hard computational tasks, so factoring and discrete logarithm. So the idea is very simple. You just take a hard task, okay, which is suitable, but that is not known, that is still secure against the quantum computer. Okay, and so there are many different approaches. The two most popular approaches are either lattice-based cryptography. Just as I said, no, lattice-based cryptography is a very interesting concept in itself, not only talking about the quantum, post-quantum thing, because using lattice cryptography, you can do stuff that is impossible using other means. For instance, homomorphic encryption, and you have you can have encryptions, and you can perform arbitrary operations with that encryptions. That could be very useful, for instance, in voting schemes and things like this. Okay, and so talking about going back to post-quantum cryptography, so in the case of lattice-based cryptography, and the problem that is used is running with errors. So it was designed by Oded Regev, I think in early 2000s. Okay, and so in this problem, idea is that you have a system of linear equations. So usually, if you think about system of linear equations, you can easily solve it. So you learn it in school or in university. But the trick that you add a small noise to your result, and then it suddenly becomes a very complicated problem to solve it. And it's possible to build a trapdoor inside so that the designer, so the person who knows the private key, he can still solve this system of equations because he knows a bit more information. But for a general person who doesn't know the private key, it's still hard. Okay, and so the leading scheme in this case is Kyber. And so it is one of the finalists from the NIST call from 2017 that was called to build like a standard for post-quantum cryptography. Because there were around 60 applicants, so different schemes. So Kyber was one. I think the only finalist so far. I think there will be some few announced later, as I understand. Okay, but it means that there is a sufficient trust in that scheme. And also, like initially, when we were talking about lattice-based cryptography, so it was like a theoretical endeavor, and the problem was that the keys were like astronomical. It was really impractical to use this, so it could be keys like measuring in megabytes, like which is like and like also very slow. But now, as I worked out, it's not the case for the Kyber. It's become optimized, and as I have learned, that if you just replace efficient elliptic curve implementation with a Kyber, so you get a slowdown of like a factor of 3, which is completely tolerable. Okay, and yeah, and so it seems that in this case the future is bright, and so it's possible to use it practically.
Okay, thank you. So since we are in actually part of a wider conference forum, 5G, let's talk a little about 5G as well. So Mattias, you're a 5G program manager at an organization, and we've all been kind of looking forward to the day when the edge computing in 5G infrastructure starts to evolve. So the decisions, some of the decisions can be made close to the mobile stations. When do you see 5G infrastructure and edge computing will be evolved so far that we need quantum resistant communications among base stations?
in my mind, quantum comes to networking in two perspectives. One is, as mentioned, that you can capture data today, save it, and then access that later when you have the capability at hand. Okay, what do I get then? A couple of years probably old information. What do I do with it? Maybe not that valuable. Now the second domain is then, okay, I'm now putting this into real use and securing myself for the future similar cases. Thinking in that direction, as mentioned, the QKD logic works between like two counterparts that share the information in a secure manner. Applying that logic to a networking logic, then a classical networking architecture consists of interfaces, that you have a number of interfaces to each other. It's similar to 5G architecture. And basically then between those interfaces you are able to apply this QKD, and depending on the need, on the risk and use case, etc. Now, if we think about previous generations, which has been much more like a blade or hardware-based establishments, then usually you could imagine a data center with a number of nodes, and then there's a number of fibers between. You can just go and take some fiber out and put their QKD-capable information exchange between the interfaces, physical interfaces. What comes to 5G standalone architecture and edge computing in combination of that, then we live in a different perspective. We live in a cloud-native environment. We live in a horizontal bus type of architecture for the interfaces, etc. So I'm really curious to see how the development of the quantum scene is approaching this virtualized networking architecture. What is the type of, they are not then nodes, but what is the type of practical implementations, measures to really attach this QKD approach in this virtualized architecture. So when, I have no idea. How even that is a little bit like not clear, but definitely there's a way now. But it will, in the end, it will depend on the risk, because all that will have a cost, and then based on that, the optimum market will probably develop the optimum where it's reasonable to meet.
Okay, thank you. So we see during this panel discussion that we are still talking about technologies that are somewhat in their early stages, and concepts, even architectures. So bringing the topics that we discussed, the mobile infrastructure, the space, the possibility of QKD currently in our national infrastructures, I'd like to conclude with one question, and I would address this first to Christoph, and then to Evijs. And let's be brief about it, because our time has, the time for questions has come already. So how do you see EuroQCI initiative progressing, and do you think it will be widely covering Europe, or what will be the coverage?
Okay, yeah, okay, briefly, EuroQCI. What is EuroQCI? The European Commission sat with 27 EU member states together with the European Space Agency and saying, okay, we want to develop and deploy a quantum communication infrastructure all over Europe and overseas territories as well. So what happened now is that, that in each member state, or not in each member state, but there are national QCIs, and in the member states are national QCIs who are developed, who should later become the EuroQCI. So each member state develops its quantum communication infrastructure, and then in the end, everything should work out together, and we'll be fine and we'll be happy. And for that, there's the project called Petrus, as a coordination support action that coordinates essentially all the national QCIs together to harmonize the efforts there. And if I may make one point here, is that as I said, so the national QCIs are developing the quantum communication infrastructure. But now, each one could, for example, develop their own architecture. But how to get and how to bind harmonizing architecture together over Europe? I think this is a very important question, and we need to see this tackled in the future. So I want to emphasize this here and maybe to make a point, yeah.
Yes, exactly. Ultimately, QKD is about trust. So how do you build such an ecosystem with multiple parties involved? Evijs, do you think EuroQCI is also on our radar?
Yes, actually, in fact, we are already several months in a real project. And yeah, again, we can talk more about it, but not enough time. But the fact is that LVRTC, together with our very important partners, we are running the national project. One of those what Christoph mentioned, and we cannot fail basically in this project. And that's not an option, but. About the standardization and putting the things together, actually, that's a big work. And the devices, the Alice and Bob, they are already coming from several vendors. But we did the test. It was 2 years ago, and 2 years ago it was not plug-and-play system yet. We don't know how it will be. We still have like almost 2 years to go. But let's see how it will go. But the nice thing is that we have a real opportunity to put like additional layer on existing infrastructure. So infrastructure is already in place, and good thing is that we have running networking equipment, what Mattias mentioned. So the network is one area, and then we are putting basically another layer on top of it, and we are not breaking the base layer. So the base layer is in place; it's very stable. So we know it. We know this universe, and we are putting just another layer. And to put things together, we are getting there, definitely.
Okay, thank you. So I hope this was interesting talk, at least interesting to me. And having these experts together on the stage, that's quite exciting, actually. Although maybe you didn't see that, but it is. It is time to get to questions that we have coming online.
Yeah, thank you. First question to the audience. Do you feel now safer on the topic to talk about it to other people? If yes, please put up your hands. You feel safer to talk about it? All right. So, by the way, it's 5 people more than before. So it's a progress. Thank you. Because it is a very complicated topic, we must admit it. And that's why one question is, how do you get financing for this question, especially if we talk about public money, for example? Is there any public money involved? And how do you talk to the people who wouldn't understand?
Well, maybe I will start. Yeah, the financing comes apparently from organizations and funds that see this as a strategically important direction to work in. And as this technology is still quite green and yet, yes, also expensive, difficult to work with. In one of the meetings in Brussels, one of the colleagues said, if not us, who then?
Yes. But then next question is, when? So when do you promise them something usable?
Okay, maybe Evijs, when we will have our national.
Well, about the financing and about the convincing, the fact is that the particular European this QSC project, the application for the project and discussions were starting before the big geopolitical change, like 2 years ago. It was before. And then the lobbying and convincing the politicians and basically the public. Okay, this is just a science, it's a nice thing, it will come sometimes, but the big change 2 years ago, we know what we are talking about. It kind of accelerated the thing because we are talking about the security. And the closer we are to the EU external border, where we are at the moment. The discussion is hotter. So we have been in many conferences in Europe, in Brussels. That's the center of Europe, right? But it's far from the border. And since we are here, it's a very good place to talk about the security. So we feel it, and that's very important.
All right, so these are also the wordings to use, because it is about security, which is really important. Question from Hassan now. Satellite cybersecurity using quantum can give more protection?
Satellites can use cybersecurity for securing the satellites, and satellites can help through quantum key distribution to secure networks over longer distances. These two things are maybe they have a different approach, but they are of course interrelated, because if the satellite is compromised, and the satellite in the current approaches to expand the quantum key distribution needs to be a trusted node, then you do have a serious problem. So we need both to secure the space assets and to use the space assets to help securing.
And then if we would have a prize to be given for most complicated questions, Roger would be the one to be awarded. What are the possibilities for integrating quantum-resistant technologies into IoT and autonomous vehicles to protect against quantum-related vulnerabilities in these interconnected systems? It feels to me it's a long, long day, but that's the question.
Mattias will understand.
No, but what is, we're talking about very capable method of gaining trust or securing the communication, and there was some examples named in the question, in the long question, about the potential application environments, but it can be something that was not mentioned either. Maybe, I don't know, defense domain, because of the sensitivity of the information that's being exchanged is maybe the trigger for its application. So in the end, I think it research and science is doing its development, and market is doing its adoption, and in the end, customer base, where the customer is willing to pay, then they meet. So I guess it's that simple.
So, and then the question, do we know all the developers of quantum computing? Do we know them?
Alexandros, do we know them?
I have no idea, yes. I really doubt it.
So one day it could be a situation when they appear and they get everything, because we know that all the data probably is accessed already.
Okay, maybe I can get like an analogy from public cryptography. For the old days of the public cryptography, they said that RSA was the first publicly known public cryptographic scheme, like, so pun intended. So this means that it was known to the general public, also being a public key crypto system. But as it turns out that it was not the first one. The first one was developed by NASA, because that, yes. And I would think that it's quite possible that we have the same thing also for quantum computers.
I have to add, whatever that means. But thank you very much. And round of applause to our panel and to the moderator. And before you go, please stay a little bit for a little closure of this event, because we have to say thank you with a round of applause, and also from our platform viewers for your patience, for being with us, either here or on the platform. We are giving a round of applause to the speakers, moderators, experts, and listeners here and online. Round of applause, please.